Aha, thank you. You can continue now. Thank you.
Okay. Okay. Thank you so much. So the differentiations focus on how quantities change or the rate at which a quantity change. So the interpretation we have it to be the derivative represent the slope of the tangent of the graph at a given point. So and it represents instantaneous rate of change, just as we said earlier. So it's being applied into accelerations because in accelerations, so when you start your car, at least you start with a particular speed, then later you can increase it. So since you are going to have a change, a rate of change there, so we use this differentiation in acceleration. We also use it for velocity. Then in economics, they use it for marginal cost and marginal revenue. So then the integration is the process of finding, or let's say that the integration is the antiderivative. That is the opposite of the differentiation. So of a function, and it represents the accumulation of a given point. So now, from the definition of the two, differentiations focus on the rate of how a quantity change around us or how a particular thing change around us. Why these integrations focus on accumulated or accumulation of a given point. So we apply this on displacement or anything that you have to like total it together because accumulation means you should total up something. So total distance, total cost, and total revenue. So these are only the prerequisites that is much needed for us to understand this differential equation very well. So the objective of today's lesson is this. At the end of the lesson, you should be able to know the definition of differential equation and distinguish between ordinary differential equation and the partial. Number two, to be able to classify differential equation into types, order, degree, linear, and so on. So number three, so enhance analytical techniques, critical thinking, and problem solving skills. So this is also very, very important for us in this course and is objective that we must to check if it's being achieved or not. So now, real life applications of ordinary differential equation. Things have been happening around us, and as we said, when we look at it very well, or what is happening around the globe, it's hardly for you to see that you can apply differential equation in it. So the number one bullet we have here is climate and environmental studies. So ODE are applied in climate modeling to understand the dynamics of weather pattern. So this is very, very important because even the professor that teaches this ordinary differential equation while we were in school, so there was a time, it's from India. So there was a time the department asked him to purchase some laptops, I think 100 laptops from India when he's coming back to Nigeria. So he helped them in purchasing the 100 laptops, he bring them down to Nigeria. So when he gave them at the department, they now realize that out of all the hundreds laptops that he bought from India, it's only 8 that was working among them. So the thing raised up a riot in the department. Some people were like saying, wow, you bought a fake laptops for us, this and that. But the man is a modeler. He know what is happening. He now asks them to calm down. That so there is what they call dynamic of weather patterns. So when you have an electronics in maybe India, for example, now, and is efficiently working there, so sometimes you might bring it to Nigeria and you see that it's not functioning well. So it happens. So we have ocean currents and atmospheric process contributing to the study of climate change and environmental dynamics. So even in this again, sometimes when we are maybe at home and we get our phone charged when it's fully charged and we travel. So the moment we change a location, when you are in the car and there is hot sun, so you realize that the battery will just be decreasing before you know. So these are the works of the climate and environmental studies. So these are models. These are the models that they use in that. So number two, we have economic and financial modeling. So they also use modeling in economic, as we said, in calculating the total cost, total revenue, and so on. So wherever you can just have anything that will just change a position from one place to another, definitely you can apply a differential equation there. So technology advancement, so engineer also use it as we said earlier. So insight into biological process. In biology, we also use differential equation for population growth. So to know the population, species, we use it in physics for you see it in waves and so on. Are we together?
Yes, we are together, sir.
Okay, so application in engineering. So ODE are crucial in engineering for modeling and analyzing systems such as electrical circuit, mechanical structure, and control system. So even in music that we listen to day, you will see that when a drummer, when he starts, you see that he's going to start whatever he's doing slowly, but before you know, so it will be increasing it, hitting this and that. So the sound there, when you when you get down and understand the techniques of what is happening or what is really happening in that music, so you realize that is a differential equation that was being captured. So in all those things, as we are going to see them in equation in our further class. So then introduction. Ordinary differential equation describe the rate at which a quantity change. So when we say ordinary differential, we'll be saying ordinary differential equation since. So when we say ordinary differential equation, that means there are still other differential equations apart from ordinary, which is very, very true. So we also have partial differential equations. We have homogeneous one, we have non-homogeneous, we have linear, we have non-linear, then so and so on. But this one is called ordinary differential equation. Why? Because it describes the rate at which a quantity change with respect to an independent variable. So this occur, or a differential equation occur when it is necessary to relate a quantity given by a function to its rate of change given by the derivative of the function. So when we hear this out, we see that it's just saying exactly what we have already explained so far from the applications, that is rate of change of quantity. So from one point into another. So an ordinary differential equation is a mathematical expression so that describe how a function's rate of change at any given point is related to its current value. So just as we said earlier, it's still saying the same thing. So what it just add up is that is a mathematical expression. So the way we write, the way we have it here, so when we come maybe to our next week class, so we see how to apply all this. So it embodies the current oh sorry it embodies the concepts of dynamic system, providing a tool to model and understand how variable evolve over time in various fields such as physics, as we said earlier, engineering, biology, economics, and so on. So ordinary differential equations are essential in capturing the essence of change and dynamics, enabling us to analyze and predict the behavior of concept system through mathematical formation. So this is one of the importance of why scientists or an engineer, why they use this differential equation is for them to be able to predict and analyze the behavior of system so over time. So classification of ordinary differential equation. Ordinary differential equation are classified by, we have order, we have type, we have degree, we have linear. So but here we are only considering in this very slide, we are considering the order for now. So ordinary differential equation are categorized by the highest order of the derivative involved and can be classified as first order, which contain only the first derivative. So, and look at it here, first order, you have it to be dy dx is equals to 2x minus 2. So, and this is what you call first derivative. Are we together?
We are together. I'm getting him.
Okay. So this is an example of derivative, that is dy dx or y prime. So it's either you write like this or you write it like this. So any one of them is accepted. So the second order involve the second derivative. And how is it going to be written? So instead of dy dx, it will be what? D square y over the x square, like this one you are seeing here now. So plus 4 dy dx plus 4y is equals to 0. So what you just need there as the second order is the d square y all over the y and the x square. And if you want to write it as the one I just showed you earlier, you write it as what? Y prime prime. Why the last one we have what we call higher order differential equation. And this include derivative of order 3 or more. So, and how is it written? It's still the same thing. Look at it here. You have it to be d cube y over the s cube. Then the second order differential equation is written as d square y over the x square. While the first order will be written as dy dx. So if you don't want to write it in this form, you use the one I just show you now on the board by writing y prime for the first order, then y prime prime for the second order, y prime prime prime, that is 3 prime for the third order, then the highest order again, up to
Okay.
n. So ordinary differential equation, as we are saying, so differential equations is any equation that involve what we call derivative, that is changing of things. So, and is being classified into two. We have ordinary differential equations. We have partial differential equation. So ordinary differential equation is one in which y is a function of one independent variable, as you can see it here. Look at the dependent variable y and x, which is the dependent variable. So when you see an equation like that, you should know that is called what? Ordinary differential equation. Why partial differential equation is the one in which this dependent variable, sorry, u is a function of more than one independent variable. So we see that from the example. But this is how it's just written. This is how it's written. You can see it is different from the ordinary differential equation. You can see the ordinary differential equation, the d there is standing very straight, while the partial derivative is somehow curved like delta. So definition: a differential equation is an equation involving derivative of an unknown function of one or more variable. So these are the examples. So you should look at the example with me together. So we have example from A to F. So we have A to be first order and so on. So, but these are just the example of differential equation. So we'll be making reference to them when we are talking about the order, type, and the degree. So these are just the examples. Any equation you just see written in this form, so it's called a differential equation. So then, how do we classify the differential equation? So the differential equation is classified in terms of types, order, degree, and linearity. So we have two types of ordinary differential equations. As we said earlier, we have ordinary and we have partial. And we have already saw how both are being written. So the ordinary differential equation, this is an equation involving ordinary derivative. In other words, a DE or a differential equation is said to be ordinary if it contains an unknown function that depend on only one variable. So look at the example now, e.g., you have the y dx. So the independent that we are having here only is x with dependent y. So when you see this type of equation, you call it what? You call it ordinary differential equation. So in the above definition, A, B, C, E, F are all ordinary. So that's why I say we'll be making reference to them. So when you check them very well, A, you can see it. Are you there?
Yes, I'm there. I'm there.
Okay. So you can see A is what? Is ordinary differential equation. Y, B also is ordinary differential equation.
See,
C is also ordinary differential equation, and F, right? So except only for E, which is not ordinary differential equation.
what of D?
Okay. Yes, and D also is ordinary differential equation. That is when you divide both sides by dx, right?
Yes.
Thank you. So number two, the partial differential equation. A partial differential equation is said, or a differential equation is said to be partial if it involve partial derivative. And we know what is partial derivative. You can have more than one function. You can have x and y, you can have x and z, and so on. So, and you'll be asked to differentiate it partially, independent of the other. So, in other words, if the unknown function depend on more than one variable. So when we look at this, we see that the independent variable here x and we have y, unlike this one that we are having it to be only
Yes.
x.
Yes.
Thank you. So when we have it, we have x, we have y. So when you have it to be that, that means that is, you call it what? You call it a partial differential equation. So where v and z are unknown function of variable x and y. So v, you can see the v here, you can see the z here. They are the dependent variable. Y, x, and y are the what? They are the independent variable. So
Variables.
we can see the difference now between the two. So to be able to differentiate between them, when you just come down here, you see one independent variable, while for the partial, you see more than one. So the order of differential equation. is order of the highest derivative in the equation. In the above example, when we go to the A and E are of order what? We just explain what is order. I even show you on the board how to write order 1, order 2. Is either you write it as dy dx or this square y over the x square, or you use it as y prime or y
Yes.
prime prime, y prime prime prime. So that is 3 prime and yn. So the order of differential equation is the order of the highest. So when you are given an expression, so you now go there and check the highest derivative occurring in your equation and you check the order. So when we go back to this A, so what is the order now of this A? We see that is of first order, right?
Yes.
So, but when we come to C, C is of which order now?
C, C is in first order, huh?
Yes, C is of which order?
First order.
Look at it again. We have
This,
d square y over the x square. So the highest derivative here is what? D square y, right?
yes.
So you say that is what? Is of order 2. A is of order
Yeah.
1. YC is of order what? Order 2. So when you come to F, so what is the order of F?
The order of F
Yes.
is like the same thing as the order of C.
Yes. Thank you. It's
Uh,
the same thing as the order of C, which is of order what?
order 2, the second order.
So now, then the degree. What is degree of differential equation? Highest of the highest derivative in the above example. So now we should not mix. This is where most students get confused between the order and the degree. So order is saying that is what? The highest derivative. Why the degree is saying the what? The degree of differential equation is the power
Of
of
the
the highest derivative.
derivative.
Yeah,
Okay.
thank you. You have to go to the what? You have to go to the highest derivative first, then you check the order before you can checkmate for the what? For the degree. So like in our example now, A and C and E are of degree 1. So let's confirm it. So
A and
A
C.
now, A is of degree what?
Degree 1.
Degree 1. Why C is of degree 1 also, right?
Yes.
But the highest derivative is 2. So, and the one that is having the highest derivative is having order of what? Is having the power of what? Power of 1. So you call it degree 1. So that is also the difference between the two. When you are checking for your order, you only focus on derivative. When you are checking for the degree, you go for the highest derivative and check their order. So the one with the highest order is your degree. So that is that on that classification. So we've classified it now based on type. We said we have ordinary differential equation and partial.
Yes.
Based on order also, and we've divided it. We've seen some example. Then degree again. So we've explained that. We've seen some example. So we can go to the next slide. Now we have the linearity. So an n order differential equation is linear if it can be written in this form. Are you there?
I'm there. I'm there.
Okay. So when you can write if you can write equation or any equation that can be written in this form, you call it what? N
Linear.
order. Yes, n order differential equation. So and it's said to be what? It's said to be linear. We have linear, as we said earlier, we have linear differential equation. So, but this is for the nth order. So you have your coefficients, look at them here, a subscript n minus 1 of x. You have this one to be a1, a naught, and so on. So why you have your y as your what, as your dependent variable, why
Yes.
we have our x to be our independent variable. So we will
Very
not
good.
spend much time on this because we still talk about it later, maybe next or next upper week. So any equation that can just be written in this form, we call it what? N order differential equation. And it's said to be what again? It's said to be linear. So
Linear
this is,
equation.
we have the y dx is equals to x plus 7.
7.
Even from our basic mathematics, when we have expression to be x plus 7, so maybe it's equals to 0. So we said the question is what? Is linear because it's not having power of anything, right?
Yes, yes.
Uh-huh. So, and a second order linear equation can be written in this form. So d square y, the x square plus, you can see that this one I'm reading out now look alike with the nth order because they will be following the same trend. So when you are in one, when you substitute n as your one, you have this. When you substitute it as two, you have this, and so on up to what? Up to the nth order differential equation. So non-linear, anyone that is not linear, as we said, or as we just show it earlier. So any equation that cannot be written in that form, in that linear form, is said to be what? Is
Yes.
said to be non-linear.
Non-linear.
Yeah, and look at the example here. Example, the y dx is equals to what? Y square.
Y.
And the y square, when you plot
Yes.
the graph, you see that this graph alone is what? Is curve, right?
Yes.
Because of the square that we're having there. So then homogeneous and non-homogeneous differential equation. So any equations that can be written also in this form, here,
Uh,
all what we were having before is equals to f of x is said to be what? To be homogeneous. If f of x in, that is in this equation 2 is what?
uh,
Is 0. Otherwise, it is called non-homogeneous. So that is simple way again to recognize what is homogeneous or what is not, what is
yes.
non-homogeneous. So when you have expression a differential equation like this form, but it's equals to what? 0. So the moment it's equals to 0, you say this what is homogeneous.
Yes.
And when it is constant, when it is not equal to 0, you say that is what is non-homogeneous differential equation.
Equation.
So look at the second example here. So dy dx plus a of x y equals to 0. So is what? Is homogeneous.
Homogeneous. Yes.
Why the second one that is equals to sine x is what? Is non-homogeneous.
Homogeneous.
Yes, because this sine x is not equals to 0, right?
Yes.
So that is that on that classification. So now we've added linear, non-linear, homogeneous, and non-homogeneous.
Non-homogeneous.
So we can now proceed again to what we call condition. So conditions, we have two type of conditions in ordinary differential equation. So, and the conditions are initial value condition. That is the number one. And what is the initial value condition? So initial is when you specify at a single point in
Um,
the independent variable or at a starting point. So when you just specify a number, that is, it have to start from what we call initial. That is the starting point, right?
the beginning, ba?
Yes. So you see your t to be equals to 0, like what you are seeing here. Y of 0 here is equals to 1. So the
Yes.
dependent variable here is 1 at time what? At time t. So that is the equations that they capture here is still at what? At initial. So you can have it also to be y prime of 0 to be equals to
2.5.
2.5. Yes, and it's also what? Is also and is also initial value problem. So in summary, we said we have two types of condition: initial value conditions, then the boundary conditions. So the initial value is when you specify at a single point or at a starting point. So you call it initial. Why the boundary condition? So why the boundary conditions? All conditions are not at one point of the independent variable. So here now they are at a single point. Y of 0, let's just say that is equals to 1. But when you come down to this boundary condition, so you'll be given something like this: y prime is equals to 2 is equals to 1.5. So the dependent variable takes the number 1.5. Why the time here is what?
2.
Thank you. That means you are following. So the time here is 2. So solutions to that, let us read it because we are not applying it today. I think by
Yes.
Monday class or Friday class, so we'll be applying them. So a function y is equals to f of x is said to be a solution of a differential equation if the equation is satisfied when y and its derivative are replaced throughout by f of x and its corresponding derivatives, or a solution of a differential equation in the unknown function y and the independent variable, say x,
X.
on the interval L, is the function y is equals to f of x that satisfy the differential equations identically for all x in I, or that belongs to I. So what this statement is saying, so from our basic mathematics, so because we come to be applying it, and that place it will be more complex than the basic mathematics we've known before. So when we said x plus 5 is equals to 10, let me repeat myself again.
Yes.
X
Uh,
plus 5, let me say, is equals to box, not 10.
box.
Let me come again. So x plus 5 is equals to 10. So, and you are asked, what is x? So what will be the answer?
Okay. In that case, you will multiply the both side by x.
So when we have x plus 5 is equals to 10. So we can definitely take the 5 to the other side, right?
Yes. Yes.
This is what I'm saying here. I think let me show you from the board. Are you seeing the board?
I'm seeing the board.
Okay. So when we have x plus, let's say, 5 is equals to,
It's supposed to 10.
let's say,
10.
10.
Uh,
So the equation or the number that will satisfy this is what? Is 5, right?
x. Yes.
Because it's 5 that you plus to 5 that will give you what? That will give us this 10 at the right hand side.
Yes.
So the same thing, that is what this statement is saying when we come to it. So a solution to the differential equations, so they are the solutions of when you put it into the differential equation. So they will give you a particular solution. So where the both left hand side and the right hand side will be what? They will be equal. So when we come to it, I think in our Friday class, so you understand it more better. This is also an explanation on it.
Okay. Okay.
Okay. So now we have started going deep into the basic of why we want to learn this course. So, and the first one, or the first essential after understanding the classification of differential equations, so the next thing to know is what we call formation of ordinary differential equation. And from the word, how to form a differential equation. So that means we can definitely have some equations which are not ordinary differential equation, but using some techniques we can form our own differential equation from them. So what is the formation all about? This involves understanding the process of deriving ordinary differential equation from physical or other problems, such as modeling the spread of a disease or the motion of a particle under the influence of a force. So all these things can be captured, and when you capture them, you can form a differential equation with them. Just like the example of a music that I just um that I just used the other time. That so when you play a music, you can decide to start with a low volume. So when you are enjoying it, you decide what to increase the volume. So it depends on what you are doing at the time. So if people are like, if you have a population in front of you, so you would like to increase the volume very well so that everybody there can hear the sound of the music at the time. So the moment you are doing that, you are changing from a position to a position, from a position to a position. So all these things can be captured using differential equation. And when you capture it as a word problem, so they can be written mathematically. So as this. So that is what they mean by deformation. So when you write it down uh, as as an equation, so you solve it. After solving it, we see the process in which we use later in solving it. So after solving it, you now arrive at a particular ordinary differential equation. So, and the prerequisite, so what you need to understand before you know how to formulate ordinary differential equations is this: proportionality. So from your variation in our secondary school, you will know what proportionality is all about, right? So the inversely proportional, directly proportional, and so on, and how to integrate the first order. So the first order differential equation. So look at this example here. So we have y is equals to a plus bx. So y is partly constant and partly varies with x. So partly constant, you have a. A is constant here, and partly varies with x. So look at it here. It's having b relating to what? To this x. So now when you integrate these expressions with the respect of z, so you have it to be what? The y, the z of this. Then the a there will give you what? Az, because you are integrating. Then the bx will give you what? Bzx. Then you add a constant. So why do we add a constant? So this will lead us to the next slide, because we have two types of constant. We have what we call a fixed constant, and we have what we call arbitrary constant. So the fixed constant, when it is being added into expressions, so it changes the expressions. Like for example, now you have y is equals to a plus bx. So if you decide to put 2 here as 2a, you can see that the a has added from 1 to 2, right? So that is what you call the fixed constant. Why the arbitrary constant? So they are the constants you add to an expressions that will not even make any effect on it. So it is not going to disturb the expression. So after that, we have method to formulate our differential equations. And the first method is count. Osman, okay. So number one method is when you are given an expression, you have to count the arbitrary constant. Like example, look at these expressions we are having in the bracket. Y is equals to ax plus bx plus c. So the arbitrary constant here is what? They are three. You have A, you have B, and you have C. Mr. Mohammed, are you there? Okay. So as I was saying, you count the arbitrary constant. You count the arbitrary constant you're having in the expression. Like for this now, you have three arbitrary constants. You have A, B plus C. So what is the second step? You differentiate the given equation to be equal to the number of arbitrary constant. So if you have your expression, the first expression given to you, if you have one arbitrary constant, you are going to differentiate it once. If you have two arbitrary constants, you are differentiating twice. If you have three, you are differentiating thrice. So continuously to the number of arbitrary constant you are having in the expression. So the number three step, you solve simultaneously the equation to eliminate the arbitrary constant you are having in your expression. So we see that in our example very soon. So number four step, resultant equation is now ordinary differential equation. So which is very free, which will be very free from arbitrary constant. So after you must have eliminate the arbitrary constant you are having in the expressions. So the resultant one, what you have last is called the ordinary differential equation. So let's look at this. We have y is equals to 4ax as our equation one. So from this equation, we have only one single arbitrary constant, which is a. So that means we are differentiating only once. And when you differentiate this, you have your y prime to be equals to what? 4a with the respect of x. So now, you now apply your own techniques. So it depends on you on how you do it to get the arbitrary constant eliminated. So here now, we divide equation 1 by equation 2. And look at it here. You have y over y prime is equals to 4ax over 4a. So when 4a cancel out 4a, you have only a single x. So then y will be equals to what? Y will be equals to x y prime. And when you look at this equation number 4, you see that it's free from arbitrary constant. For that reason, is ordinary differential equation. So the second example we are having,
Eh?
Mr. Mohammed.
I can hear you, sir.
Okay, are we together?
Yeah, we are together.
Is there any question?
No,
Okay, in the absence of question, we can continue with the example number 2. Given equation of this form, y is equals to ax square plus bx square plus cx plus d. So this is our initial expression. So we now count based on the steps we highlighted before, that after the expression, you count the number of arbitrary constants you are having in your expression. And for this one, you are having it to be 4. So you are going to differentiate 4 times. The first the derivative, the second derivative, third derivative, and the last one. So the first derivative gives this. When you differentiate with the respect of x, you have 2x. With the respect of x also here, you have your 2x. With the respect of x here, you have nothing. And the constant will give us 0. Then the y prime prime, the second derivative. So when you differentiate this again, with the respect of x, you have 2a. With the respect of x, you have 2b. Then the constant also will give us 0. The third derivative, so we realize here that we are not having any independent variable x anymore. So all we are having here is constant. So when we differentiate constant, we'll be having 0, 0, 0. So when you have 0, the fourth derivative definitely will give you 0. And it's obvious and it's very, very clear that the last one is very free from arbitrary constant. For that reason, it is ordinary differential equation. So the implicit example, why we call this implicit example is that the expression we are having here is equals to an arbitrary constant a. So, and which is very, very easy. So we are only differentiating once because the arbitrary constant here is only a. So when you differentiate this x cube, we are going to have 3x squared dx minus, when you differentiate this, you have 6x y dx. So, but here you are having x and y as your relating to each other as the independent variable here. So you now differentiate it partially. So for the y, you have 3x squared, then y will be gone because you are differentiating with the respect of y. Then the y is equals to 0. And 0 is from the constant because when you differentiate constant, you don't have any variable here. So to differentiate it with, so with differentiating constant, will give us what? Will give us 0. And that is our objective because we want to eliminate the arbitrary constant. And since the arbitrary constant is gone, so we just do the remaining simplification and we have our ordinary differential equation. So from this, we have our the x here. So putting them together and factorizing the x outside, you have x minus 2y, the x, minus x, the y. So that is when you divide the 2 by 3. So you divide it by 3. So this is what you have. You have equation 3. Then lastly, you have it to be x minus 2y dx minus x dy equals to 0. And this is the last expression. And the last expressions give us our ordinary differential equation. Any question? Okay, in the absence of any questions, I think you can continue. So example number 3, we have the expression to be y equals to ax squared plus bx. So just as we've been doing from the 2 examples we've solved earlier, you count the number of the arbitrary constants you have, and that is the number of times you are going to what? You are going to differentiate them. Here we have 2 arbitrary constants. So differentiating it, first you have the first derivative to be 2ax plus b. The second derivative will give us what? 2a, which is our equation number 3. So now you have this to be d square y, the x square, the second derivative, to be equals to 2a. So how do we now join them together? So from the steps, we said we solve them simultaneously. So substituting 2a into our equation 2. This is our equation 2. So what will happen? So this is what we are going to have. So substituting it, we have this equation number 4. That is the y dx is equals to x. So instead of putting 2a, you put d square y over the x square, then plus the b we are having in the equation 2. And we have it to be equation 4. So from there, we can make our b to be subject of the formula. So after making the b subject of the formula, we have this, because we just only take this to the both side. So taking this to the both side, or subtracting x d square y over the x square from both sides, we have our b to be this. So from our equation 3 also, we can find a value for the a. And the value for our a is nothing but a will be equals to half of, because you divide it by 2. Dividing both sides by 2, you have it to be half d square y dx square. So now, substituting a and b in equation 1, that is the initial expression. So substituting it, we have this. So when you have this combining expression, when you multiply it out, that is multiplying x by this bracket, you have this equation number 6. So when you have the equation number 6, simplifying it further, when from this, you see that this d square y and d square y here are common, so you can factorize them. When you factorize them, you have it to be this. When you now take the LCM of this bracket, you have your final answer to be x squared over 2, then d square y over the x squared, which is the final differential equation. So going through these, because they are already this, they are there, so they are there. We solve it step by step, and it's very straightforward. So when you go through it, so you have any problem with that, so you can just message me privately and ask, and your questions will be attended to. So the last from our today's class is this. So we have these expressions to be the one we'll be having before. We've not solved anything concerning trigonometry. So, but our last examples talks about that. So our expressions here is y is equals to a sine x plus b cos x, which is our initial problem. So as we highlighted earlier, the step in which you are using in solving it is what you also use in this trigonometry example. You count the number of arbitrary constants, and the number of arbitrary constants here are 2, a and b. So definitely you are differentiating twice. You have the first order, you have the second order. So when you differentiate this expression, you have what? Differentiating with the respect of x, you have dy dx equals to a is arbitrary constant. You write it down as a constant. When you differentiate sine x, we have our cos x. So when we differentiate our cos x, we are going to have what? Negative sine x. That is why this sign is changing from positive to negative. So then we have the first derivative to be this: dy dx is equals to a cos x minus b sine x. We now go to the second derivative just because of the second arbitrary constant. So d square y over the x square is equals to Differentiating cos x now will give us negative sine x. And we have a negative already here from our equation 2. So differentiating sine x will give us what? Positive cos x. So the sign will not change. So we have okay, as I was saying before, I admitted a colleague into the all. So I said, so the second derivative give us minus a sine x minus b cos x. So having this, and when we now consider the initial problem we have, we see that the second derivative and the initial problem we have from our question 1 are the same thing. So the only difference is that this one is positive all, while this one is what? Negative. So this expression here can be written in this form. So therefore, d square y over the x square is equals to negative y, because our second derivative has already given us the equation 1, but in negative. That is why we are having it to be negative y. So taking this y back to the left hand side, we have it to be this d square y all over the x square plus y is equals to 0. So, and this give us a differential or ordinary differential equations. And this is the last example we'll be taking for today. So in our next class, we solve, if there's any questions, we attend to it first pertaining to what we have learned today. Then we take more examples again. So uh, from other types of differential equations and solve them. So in summary, today we talk about differential equation. Differential equations is equations that involve derivatives. So then the classifications is classified into order, into degree, into type, into linear, homogeneous, and non-homogeneous, and so on. So we show some examples of what we mean by when a differential equation is said to be of so order. So we have order 1, order 2, up to order n. Then we have type of differential equations. We talk about ordinary differential equation and partial differential equation. Then we talk about the degree of differential equations. And we say the degree of differential equations is the degree of the highest derivative from an expression that we have. So we talk about that also. So we show ourselves when an expression is said to be linear differential equation. We show non-linear differential equations. Likewise, homogeneous, we talk about homogeneous when a differential equation is said to be homogeneous. We show that. Then the last one, when an ordinary differential equation is said to be non-linear equations. So is there any questions? Because it's already 6:49, we only have some seconds to go. So is there any question? Okay. In the absence of any questions, I think we can call it a day for today. We meet again on Friday. Thank you very much.